The discussion about the TD algorithm is not yet complete. Another important point is, what does this TD algorithm do mathematically, and why does it take this particular expression? Earlier, I directly presented the TD algorithm, but why was it designed this way in the first place? What exactly is it doing? Let's analyze this. Mathematically, it is actually solving a Bellman equation. Whose Bellman equation? The Bellman equation of the given policy. When we introduced the Bellman equation in a previous lecture, we already introduced algorithms for solving it. So, why do we solve the Bellman equation again? What is the difference? The algorithms we introduced earlier were model-based. Now we do not have a model, so the TD algorithm solves the Bellman equation without a model. I hope everyone can clearly understand this point. What we do next is to mathematically prove what I just stated. The first thing we need to do is to introduce a new expression of the Bellman equation. This new expression of the Bellman equation is actually very simple. Let's take a look at it. What is this? This is the most basic definition of state value. Starting from state S, the state value is equal to the expectation of the immediate reward plus the return obtained after transitioning to the next state. This expectation can be split into two parts: the expectation of the immediate reward, ER, and the expectation of the discounted return, EG. This EG can be further written in this form. If the next state is S prime, then we take the expectation of its state value. Therefore, these two forms are equivalent. The definition of the state value we just mentioned can be transformed into this equation. On the left side, we have V pi S, which equals ER, plus gamma V pi S prime. This is also a Bellman equation. Compared to the Bellman equations we studied in a previous lecture, this one has a more concise form. Why? Because it contains an expectation. If we expand this expectation, the equation becomes identical to the ones we introduced previously. Sometimes this equation is called the Bellman expectation equation because of the expectation term it has. The reason I am introducing this Bellman equation is that our TD algorithm essentially solves this equation. Why? Let's continue to explore. Next, let's solve the Bellman equation we just derived. How do we solve it? We use the RM algorithm introduced in the previous lecture. You will then see that the RM algorithm here is very similar to the TD algorithm we discussed just now. Through this, we can see that the TD algorithm is a special RM algorithm for solving the Bellman equation. To solve this Bellman equation, we first define a function GVS. If we write it as GW, it might be clearer. We aim to solve GW equals 0. Here, W has a specific meaning. It is Vs, the estimate of V pi S. So we use the slightly more complex symbol GVS instead. Setting this to 0, we get Vs equals this long expression following the expectation. This is V pi S, meaning V pi S is a solution to this equation. How do we solve this equation? We can obtain the samples R of R and S prime of S prime. Using these samples, we form G tilde. This is a typical formulation for RM algorithms, which we will quickly review. So G tilde equals Vs minus R plus gamma, V pi S prime. This essentially is GVS plus a measurement error. This is the typical formulation of the RM algorithm. Replace G tilde with the sampled values resulting in the following form. Take a close look at this equation. It is very similar to the TD algorithm we introduced earlier. However, there are two small differences. Let's examine them. The first difference is that here we repeatedly sample R and S prime. Essentially, we start from S, obtain R, and transition to S prime. At the next moment, we start again from S, obtain R, and transition to S prime, because we need repeated sampling. This differs from the TD algorithm, which uses a temporal sequence of visits within an episode. We will discuss how to resolve this shortly. Another issue to note, which I have marked in blue, is that to calculate Vk plus 1, I need to use V pi Sk prime, meaning the true state value V pi of Sk prime. However, we do not know V pi. What should we do? I will address this issue below. To resolve the first problem, we need to replace this set of samples with this sequence. In short, instead of starting from S, obtaining R and S prime, and then starting again from S, obtaining R and S prime again, we obtain a trajectory. If we happen to visit S in this trajectory, we update the value of S. If we do not visit S, the estimated value corresponding to S remains unchanged. This way, we can use a trajectory or sequence to update the values of V for all states S. The second problem is that we do not know V pi S prime, which is what I am trying to estimate. What should I do? The solution is simple. Replace V pi S prime with Vk S prime k, which is the estimated value Vk for state S prime. A question that follows is whether we can still ensure convergence when using the estimated value Vk to replace the true value V pi. The answer is yes. An intuitive explanation is that we only have one equation, continuously updating the value for each state S. If written in this form, each state has an estimated value. Although the estimate is inaccurate at present, it is continuously corrected. Eventually, all state estimates will converge to V pi. This is the idea of using the RM algorithm to solve the Bellman equation. While the above discussion is relatively intuitive, we will provide a rigorous convergence analysis below. The strict convergence result for the TD algorithms is as follows. The theorem states that VTS will eventually converge to V pi S if this condition is met. This condition is about the coefficient alpha t. If you have studied the RM algorithm or the stochastic gradient descent algorithm in our previous lecture, you will find this condition familiar. I will not go through the proof of this theorem here. You can refer to my book for detailed explanations if you are interested. Based on this theorem, let's highlight a few points. First, what does this theorem actually say? It says that the state value estimate will converge to the true state value. Thus, the TD algorithm essentially performs policy evaluation for a given policy. How do we improve this policy to find the optimal policy? The ultimate goal of reinforcement learning is to find the optimal policy. Later, we will introduce how to combine policy evaluation with policy improvement to achieve this. The condition about alpha t, it should satisfy these two equations. The first equation states that the sum of alpha t should approach infinity. Note that this should hold for any state S. What does this mean? It means that each state S should be visited infinitely many times. In practice, it just needs to be visited many times. Why is that? Whenever a state is visited, the corresponding alpha ts is a positive number. Alpha ts for the unvisited state is 0. So the sum of alpha ts being infinite implies that the specific state is visited infinitely many times. Additionally, this condition requires alpha t to eventually converge to 0. However, we usually set alpha t to a small constant value in practice, such as 0.00x. Then this condition cannot be strictly met. But why do we do this? Because real-world situations are complex, and we want the experiences obtained later to still be useful. If alpha t eventually approaches 0, those later experiences become useless. So we set it to a small constant value instead of 0. We discussed some important properties of the TD algorithm just now. Next, let's compare TD learning with Monte Carlo learning. Monte Carlo learning was the first model-free reinforcement learning method introduced in this course, and the TD algorithm is the second. What are their respective advantages and disadvantages? Let's discuss their pros and cons one by one. It is worth noting that besides TD, I also included SARSA here. What is SARSA? It is an algorithm we will introduce later. The expression of SARSA is almost identical to the TD algorithm we discussed just now, so I included it here for comparison. The first property is that the TD algorithm is incremental. What does this mean? It means that as soon as I receive a reward and transition to the next state, I can immediately use this information to update my current state value estimate. In contrast, MC learning is non-incremental. What does this mean? Although I am currently sampling and receiving data, I cannot use it immediately. Why? Because I need to keep waiting until the episode ends. Then I can calculate the return from the current state to the end. I use that return as an estimate. Because TD is incremental, it can handle continuing tasks. It can also handle episodic tasks, so it can handle both. What is a continuing task? It is a task that does not stop and continues indefinitely. To update in such tasks, I need to update incrementally, because I cannot wait for it to end. While there are no truly endless tasks in practice, you can imagine very long tasks. MC learning, being incremental, can only handle episodic tasks. It requires the task to stop before the MC algorithm can be used. In these aspects, the TD algorithm is better. Next, let's look at another property of TD algorithms. It is bootstrapping. Bootstrapping means that we already have an initial guess for the state value. Based on this initial guess and some new information, we can get a new estimate. In contrast, MC learning is non-bootstrapping. Why? It directly uses the return calculated from the current episode as the estimate for the state value without involving previous estimates. Another property is that the variance of TD estimation is relatively low. Why? Because the algorithm involves fewer random variables. For example, starting from the current state, we get a sample of the reward and a sample of the next state. If it is SARSA, it will also sample the next action. But overall, the number of random variables involved is small. Therefore, using fewer samples would result in a relatively low variance. On the other hand, MC learning involves many variables. Why? Because it requires an entire episode. In this episode, there will be a reward in the first step, a reward in the second step, and a reward in the third step, with many random variables coming in. Since I have many random variables and I only use a single sample, the variance of the estimation is relatively high. Let's illustrate this with a straightforward example. Suppose the length of an episode is L, and let's say this length is 100. For each state, there are 5 possible actions. This means there are actually 5 to the power of 100 possible episodes. In other words, starting from the current state and randomly sampling, there could be 5 to the power of 100 such episodes. However, if I use only one episode to make an estimate, you can imagine that the variance would be high. Random variables have 2 properties, variance and expectation, or called mean. While the variance of TD estimates is low, the mean or expectation has bias. Why? Because it is bootstrapping and relies on initial estimates. If the initial estimates are inaccurate, this inaccuracy introduces bias into the estimation process. However, as more data is collected, this bias diminishes. In contrast, MC learning, despite its high variance, has unbiased estimates because it does not involve initial estimates. The expectation of its estimates equals the true action value or state value, making it an unbiased estimator.